Okay, finally got it up and running. This one. Minimize, maximize. Cool. So we're working on the project number 4, at least schedule-wise. Goal is get it in before we all disappear for Thanksgiving. Finally get a break. 4 weeks too late, but we're getting a break. How's it going so far? Anything coming up yet? Nothing yet? One note about like the stiffness matrix, it's really, this is like a Newton per millimeter, so E and A should be megapascal and millimeter squared. So what's the cross section? You can use Newton. You could use Newton per meter squared and meter squared, but then you have to change like the units that are in here. Like we need a set of consistent units. But anyway, this whole thing is all like, I think it's a 1/millimeter scale. Everything inside this big 14 by 14 K matrix. And on Monday, I was talking about like what came from that extra material. Like another variable called nodes describes where each one of the 7 parts of our truss are located. And they're all 300 millimeters apart. So it's all equilateral triangles, length of 300 millimeter. But we can see this. So if we wanted to plot nodes : 1, nodes : 2, make all those squares. It would help if I could put everything. We can see like these are the locations before any loads, so it's describing geometry before you apply load. And then I like to say axis equal, so it actually looks like equilateral triangles rather than yeah, there's that, and then there's also LMs. And that's describing like how each element is connected from one node to the next. So 1 to 2, 2 to 3, and then 1 to 3, and then 2 to 4, kind of moving around like that. I wonder. I don't know why it's telling me, giving me a problem. I just wanted to throw text in there. There we go. I was just trying to label each of the nodes 1, 2, 3, 4, 5, 6. So I went through each row of nodes, well, like from 0 to 6, and just grabbed what's the location and what's the label. Oh, okay, yeah, like added label for each, yeah, that works. Yeah. I think you have to manually change the colors. Like there's different ways of like creating color spaces. So you can, like that's one way of using you have 14 things. Alright, give me 14 colors in this color space. Yeah. That works pretty well. Yeah, I haven't found a way to change what colors and cycles. is something, it just keeps cycling through your own color spectrum. You get it like 50 people. Yeah.
It was like this.
Oh, that's cool.
Yeah, but I understand what's going on.
I think it's just running like one at a time.
Yeah, I think so.
Yeah, it looks like it's
How big?
there's a magenta. It's a common. Yeah, trying to. Ooh, okay. Nice. Yeah, okay. It'll let you define your like post-processing function from the same way. Goes that speed. Yeah. It's, looks like it's moving a lot for speed. You have two different view solutions.
Yeah. Yeah.
That was two. That looks like good. So it's funny, today colors came up in two. And so one of the reasons that I love Matplotlib is that their documentation is awesome. There's just so many examples of like anything that you want to do is somewhere in this like giant website full of examples and all sorts of stuff. So they're like if you're looking for all these different like magenta versus fuchsia and orchid, I think we can call those right in there. Let's see. How do I? Fuchsia, if I can spell it. Fuchsia. Yeah, nice. So if you want like a list of how many different colors can I have, we could just grab this and dump it in here. Oh, color table not defined. Oh, I see. So I'm gonna grab this whole thing. But there's all sorts of cool stuff. And I wonder if there's a way that I can get M colors. Cool. So create that M colors creates like a dictionary of all the different colors from CSS4. And I'm trying to figure out, is there a way I can grab, I mean, I know I can just say like silver. How do I get all the values? Got keys. Oh, look at that. So if I wanted like a list of every CSS color, like cascading style sheet color, I could grab all this stuff and plug it into, like, here's a list of every color and I want to cycle through each of those colors. Some of them are a little similar, right? Gray versus gray. Like GRAY versus EY. They look like the same color to me. Could be wrong, but I think they're the same. I think it's the same thing. 80, 80, 80, and 80, 80, 80. I think it's just the two different spellings of it. But you could grab that list of stuff, like all the keys. And we could manually say, like, here's my list of colors. Trying to see if I can change the color. Yeah, I should be able to. It's hard to read, but I did change the color of all the text, and it'll keep changing the colors every time I run it because I just keep adding one to the eye color. What did you use for finding like LU and then solving that LU decomposition, like forward backward substitution? We didn't talk about this too much in class. PLU, my bad. Do you know what this P matrix is? Like if you get an LU decomposition, there's P, L, and U. So this one has to do with like the partial pivoting, so switching rows. In this case, if it's all ones along the diagonal, then we already have like everything's in a good order anyway. And the way I built this FEA problem, coming back, I organized the nodes in a way, like I could have numbered these nodes in any order, but I made them in a way that it would be easier, that we would have less problem solving it. And that's kind of a cool part about meshing, is like you can mesh, as you create a mesh for a finite element routine, you can do it in a way that it's going to make the actual solution easier to do without knowing anything about what the boundary conditions are or the loads applied. Like it's just based on how things are organized in the problem. So that's what I did, and that's why, not to brag, but our pivot matrix is it's a identity matrix, which means I did a pretty good job in creating this geometry mesh. And then L, here, let's just look at like the first 3 rows, 3 columns. L always has like ones along the diagonal like this, and then everything below can be zeros or some kind of fractions. And then meanwhile, our upper is going to have like non-zero diagonal terms and then something filling up that upper triangular matrix. Main goal is that, like, if we just had this 4x4 matrix, the last equation in our upper triangular matrix is just 0.003 times x4 equals something, and that's pretty easy to solve because everything else is a 0. And then once we have that one, we can plug it into this part because we know from the bottom one, we know the next one up. And then we have two things, and we can plug it into the third equation. Same thing with that L. It's just now we're working our way down instead of working. So we're doing back substitution with that upper triangular and forward substitution with the lower. Would probably help to have actual stuff in here, right? What are we doing? Negative 300. So when I solve this problem, like lower is my right-hand side. Really, I should be using like, take that pivot matrix, multiply it by F to rearrange my right-hand side. It's all diagonal, so transpose of that identity matrix is the identity matrix, but for good practice, this is what I should be doing. Do these numbers mean anything? Like what is that output for Y? Like, are these displacements or forces or strain? Like, does it have any real? Not really. This is just like an intermediate. I need to know what this is so that I can plug in the next thing and say that I guess I should have, let's call it U free, like. So now I actually get like, what are the displacements of of each one of the nodes? At least the ones that I said that can move, like the ones that were free to move. Because I also have I also have boundary conditions that say node 1 has to be 0 and 0. And then node 2 moved by 6 millimeters on the x-axis and negative 6 millimeters on the y-axis. And then node 3 moved 1 millimeter right, but 12 millimeters down. Node 4, 3 millimeters to the right, negative 16, so 16 millimeters down. And then 5, negative 12. And we were just taking a look at, sorry, I'm scrolling up and down a little bit here. We were just taking a look at like where those nodes were to begin with. So if I want to look at where are they now, where are they now? I could add all of the U total. So here I want to do start at 0, but skip every other one. And here I want to start at 1 and skip every other one. So I can grab all the X locations and all the Y locations and add those to where they were to begin with. And instead of fuchsia, what other colors we got? Let's go with like a deep sky blue. And now I have pink saying where they used to be, and then deep sky blue of where they went. Where are they now? So we have an answer, like, so if we only have 0.1 millimeters squared, pretty small, pretty thin kind of truss structure. But what if we only want to move, the max deflection is 0.2 millimeters, so 200 micrometers. Then how do we figure out how much area we need to use? First off, with 0.1 millimeters, what's the max? What's our total Y deflection? How much did it move? We have like all the displacements here. How much did it move? What's our total deflection? Did you already figure it out, or what is total? Okay, that's why I'm asking. Like, so what is, so currently, like, how much did it deflect? What's our total deflection? It seemed like people were trying to wrap this part up. Which one?
Is it just like the biggest number?
Biggest number? Yeah.
Well, you add all
So like if you think about like a bridge, like, okay, apply a load, what was total deflection? It's just going to be like, what was the biggest number? Like, how much did the whole thing change as a whole? So we're just looking for absolute value. What is the max displacement? So here in this case, negative 16. So I want that number to be 0.2. And there's more than one. We've looked at a few different ways of doing this. One is just keep guessing, like keep plugging in new areas until you get the right one. Another one is you could set up a function where this output is subtracted from 0.2, and until it becomes 0.2, you just you use like Newton-Raphson or something, like create some kind of method. But if, so here, let's try this. If I double this area, so I went from 0.1 to 0.2, and that max displacement is now -8 instead of -16. So doubling the area decreases displacement by a factor of 2. And that's because we're doing a linear algebra problem. So it always scales. Like if I take the right-hand side and multiply it by 2, then my answer has to be double that result. So make it half. It's going to be half the displacement. So what I could say is, what is this one? Number 5? No, number 7. $40? Does that sound right? Doesn't seem right. So if I'm looking for like the new area, I can say like, all right, well, what's the ratio of that displacement to my desired displacement? Because it's a linear problem. And what did I get? 8.06. Sure enough, now my max display, I can't even see, at this point, I can't see these things deflecting, which is pretty typical with like with a finite element. Like usually displacements are very small compared to how big the structure is. But that max displacement is exactly 0.2. So I want the area to be at least for steel, at least 8 millimeter squared. So if there's a choice between 8 and 9, we'll go with 9, and plenty. Cool. Anything else? right, like looking into last parts of the semester. Right now, we're trying to wrap up project 4. Next week, we have off, finally get a break. And then when we come back, this week of, first week of December, you can do one of two things. You can either go back and revise modules 1 through 4, like any of those homeworks or projects, based on feedback that you got from TAs. Or you can take a look at homework 5 and project 5, and those are due that Friday before finals. If you're trying to get it done and this last week is full of projects, and let us know, and you can submit during finals week for homework 5, project 5. Only thing about like finals week is there won't be any resubmissions during finals week. Like there won't be feedback to resubmit anything. So by the time we get to that, we're just sort of like, whatever you turn in, that's it, we're done. We gotta wrap up, get grades in, move on. Sound like a plan? No final, just one more project and some bonus work if you want. Cool. No other questions? Nothing? Too quiet. Should be something coming up. All right, have a great break. Hopefully I'll catch you before finals week. Thanks.